Although we have studied the voltage regulation of a transformer, why you are going to calculate the voltage regulation is, as the load is increasing on a synchronous generator, the terminal voltage will be decreasing. So how much the terminal voltage will be decreased for given amount of the load, that we should know before going to use the generator. That's why we are calculating the voltage regulation of a synchronous generator. So before going to entering into the voltage regulation, let me see what are the different parameters of a synchronous generator. This is the rotor on which the DC winding is placed. Whenever we are given excitation, the poles will be created, that is north pole and south pole. Because of the north pole and south pole, the constant flux will be created, that is shown with a arrow. So whenever we are given a mechanical input, the rotor will be rotating, nothing of the flux also will be rotating in a space. There is a rate of change of flux linkage with a stator winding. The sinusoidal voltage will be induced in a stator winding. So because of the stator winding is a three-phase winding, which are displaced by 120 degrees, the voltage induced in the stator winding is a three-phase voltage. That voltage we can take outside from the three terminals. If we connect any load here, now the current is passing into the stator winding. When the current is passing through the stator winding, the winding has a some amount of resistance which is opposing the flow of current. That we represented as a stator resistance or armature resistance. That simply represented as a RA. So when this flux is rotating, there is some amount of voltage will be induced in stator winding. That is nothing but a no load voltage or the excitation voltage. That we represent with the E0 or ER. Now the current is passing through the stator winding. There is some amount of flux will be creating and linking with the own turns. That flux is nothing but a leakage flux. That is also sinusoidal nature. So because of the flux, the voltage will be induced in stator winding. That physical phenomena we represented as the stator winding has a leakage reactance of XL. So one more parameter is come to the picture. When the current is passing through the stator winding, a flux is creating, that is affecting the main flux, nothing but armature reaction. The armature reaction we represented with a XA. So because of the armature reaction, there is some amount of voltage will be dropping in a stator winding. That is depending upon what type of load we connected across the generator. That voltage drop will be we represented with a XA. See here, armature reaction reactance and a leakage reactance. These two highly depending upon the armature current. V is nothing but the terminal voltage which is across the load. E0 is nothing but no load voltage or the excitation voltage. These are the different parameters what we can see for the stator winding during the operation. Now we are going to develop the equivalent circuit of a synchronous generator. Since it is a three-phase mission, we are going to develop the equivalent circuit only for the per phase. This is the excitation voltage E0. This is the armature reactance. This is nothing but a leakage reactance. The sum of these two is nothing but a excess, nothing but synchronous reactance. This is the armature resistance. IA is nothing but armature current. This is nothing but a load. V is nothing but a voltage across the load. Now we are going to find out what is the relation between the E0, nothing but excitation voltage and load voltage. So to find the relation, we have taken the load as RL load which is connected across the synchronous generator. Now we are going to develop the phasor diagram. So first we have taken the IA, nothing but armature current on the x-axis. This is IA. All phasors are rotating in anti-clockwise direction. When we connect the RL load here, this current lags the voltage, this voltage by some angle. So we have to draw the VA here. The voltage across the load V leads the I by theta angle. Now for this quantity we are adding IA drop, that is in phase with a IA. So from the tip of the V, we have to draw the IA vector. The voltage drop across the axis, that is nothing but a JIA axis. The angle between the resistance drop and reactance drop is 90 degrees. So perpendicular to this vector, IA vector drawn. Phasor sum of these two is nothing but a IAZS, nothing but the voltage drop in this branch. Now we are adding this voltage drop to this voltage across the load, which gives the E0 or excitation voltage. Now we are going to find out what is the relation between E0 and V. Now from the triangle O, this triangle, this is the right angle triangle. This is the right angle triangle. See here one more right angle triangle is there. This is also the one more right angle triangle. Length equal to IRA. Now this length equal to, from this triangle, this length equal to V cos theta. V cos theta plus IRA is nothing but this length. The same manner, this length equal to V sin theta plus IA excess. Nothing but this is total length. This is the right angle triangle. E naught square equal to this length square plus this length square. So finally you are getting the E naught equal to EF equal to square root of V cos theta plus IRA whole square plus V sin theta plus or minus IA excess whole. See, by using this formula you can find out the per phase excitation voltage in stator winding. IA is nothing but armature current. Here the plus is used for the lagging power factor, whereas the minus is used for the leading power. This is the phasor diagram of a synchronous generator when we apply the RL load across the generator. Now we are going to see the phasor diagram of alternator or synchronous generator when we connect a resistive load. Whenever we are saying the resistive load, the current is in phase with the voltage. So here we are getting the IA, that is in phase with the V. IRA drop you have to add for this one. This is IRA drop. Perpendicular to this one you have to draw a JIA axis. This is JIA axis. Phasor sum of these two is nothing but a IA ZS. Now the phasor sum of V and IA ZS is nothing but a excitation voltage. This is the phasor diagram of the synchronous generator when we connected a resistive load across the generator. So already we explained this phasor diagram with a lagging power factor. Now we are going to see the phasor diagram of a synchronous generator with a leading power factor. So whenever we connect a capacitive load across the generator, current leads the voltage. Now here we have taken, this is V. IA we have taken on the x-axis. Here we have taken the IA. All the phases are rotating in anti-clockwise direction. So this angle is nothing but a theta. Now on the x-axis we have taken the current. For V we are adding the IRA drop. So this is IRA drop is always parallel to the IA. That we have to draw from the tip of the V. So this is nothing but a IRA drop. Perpendicular to this one you have to draw a JIA axis. This is JIA axis. Now the phasor sum of these two is nothing but a IA ZS. If you find the phasor sum of V and IA ZS is nothing but E naught or excitation. This is the phasor diagram of a synchronous generator when we apply the capacitive load across the generator. Now we are going to define the voltage regulation of alternator. The voltage regulation is defined as change in the terminal voltage from no load to the full load. It is represented with a no load voltage. It is nothing but a voltage regulation. As the load on the generator increases, the terminal voltage will be decreases. That is highly depending upon how much load we connected, and what nature of load also, whether it is a resistive load or the capacitive load or inductive load. Generally, it is represented with a percentage value. Now, the voltage regulation is equal to no load voltage minus terminal voltage at full load divided by the no load terminal voltage. So, percentage VR equal to E naught minus V by E naught into 100, where E naught is nothing but a no load voltage or the excitation voltage. V is nothing but a terminal voltage at a full. There are different methods we are proposed practically to calculate the voltage regulation of a synchronous generator. The first one is the EMF method or synchronous impedance method. The second one is the zero power factor method or Phasor triangle method. Third one is the MMF method or ampere turns method, by means of which we can calculate the voltage regulation of a synchronous generator. That we are going to see in the next coming classes. Thank you very much. If you have any doubt, you can ask me directly or you can ask in the comment box of the YouTube channel, so that I am always welcome to answer all